Every day, your brain encounters conflicting choices and instantly computes a resolution. The central hub managing this friction sits deep inside the brain's anatomy. That hub is the medial frontal cortex, or MFC. It monitors our actions and signals the need for adjustment when we face competing alternatives. Studying the MFC presents a persistent mechanical problem. Functional MRI scans provide excellent spatial mapping, showing us exactly where activity occurs. But fMRI captures blood flow changes that take seconds to resolve, making it too slow to record rapid millisecond by millisecond neural firing. Standard scalp EEG sits at the opposite end of the spectrum. It records electrical timing perfectly, down to the millisecond. However, measuring through the skull blurs the signal, making it difficult to pinpoint exactly where deep inside the cortex that electrical activity originated. We are left with a persistent gap in our data. Researchers can see where a decision happens, or exactly when it happens, but rarely both at the same time. To map the mechanical sequence of how the brain resolves a conflict, we require an approach that captures both spatial granularity and temporal speed simultaneously. Decoding human decision-making requires direct access to the deep circuitry of the medial wall as it processing competing information in real time. A rare window into this region comes from intracranial EEG, or IEEG. In specific pre-surgical evaluations for epilepsy patients, doctors place electrodes directly inside the living human brain. This schematic shows macroelectrode strips implanted directly along the inner wall of the MFC. Researchers utilized this existing clinical setup to test cognitive control at the source. While monitored by these internal electrodes, the patients performed a modified flanker task. The task forces the brain to process conflicting directions. In congruent trials, a target arrow points in the same direction as the arrows surrounding it. In incongruent trials, the target arrow points the opposite way, forcing the brain to suppress the distracting visual noise and select the correct physical response. These bar charts display the behavioral performance. Look at the gray bars, indicating the incongruent trials. Reaction times increase significantly when the arrows conflicted, jumping from 726 to over 850 milliseconds. Patients maintained near-perfect accuracy during these slower trials. The reaction time delay is a direct measure of the brain monitoring and resolving the conflict. With the task inducing measurable cognitive friction, researchers finally had an unfiltered, high-resolution view of the deep MFC nodes, dynamically struggling with a choice. Recording directly from the cortex produces a high-resolution stream of electrophysiological data, which researchers compile into time-frequency spectrograms. These plots map the timeline of the trial horizontally and the frequency of the brain's electrical oscillations vertically. These plots and brain map show the MFC's electrical state roughly 300 milliseconds after the arrows appear, right before the patient presses a button. Notice the heavy blue regions. This represents a distinct suppression of electrical power in the beta band, between 15 and 30 Hz. Geographically, this drop is concentrated in the posterior dorsal electrodes. In neurobiology, a localized suppression of beta oscillations indicates a decrease in global neural coherence. The brain is dampening its motor networks to process the environment and plan a physical movement. By shutting down beta activity, the back of the MFC acts as a targeted braking system. It stalls the motor cortex to prevent a premature response when the arrows conflict. Once the brake is released and the physical choice is executed, the electrical landscape of the cortex shifts. Looking at these lower brain maps, we see the frequency data captured in the exact milliseconds immediately following the user's physical response. The dominant feature is a localized surge in power within the theta band, between 4 and 8 Hz. Geographically, this enhancement radiates from the anterior electrodes at the front of the medial wall. Medial frontal theta carries a highly specific function. It drives outcome evaluation and post-response monitoring. The data shows this post-response theta firing significantly stronger during the incongruent trials. The brain is actively analyzing the difficulty of the conflict it just resolved. The moment the action concludes, the front of the MFC takes over as an outcome evaluator, utilizing low-frequency theta waves to verify the accuracy of the completed choice. We see high-frequency beta suppression in the back and low-frequency theta enhancement in the front. The data forces a question. Is this spatial separation a rigid architectural rule of the brain? These scatter plots correlate the two distinct frequency bands across every implanted electrode. The vertical y-axis plots pre-response beta suppression, while the horizontal x-axis tracks post-response theta enhancement. The results reveal a strict negative correlation. The specific electrodes that exhibit the most pronounced beta suppression before the choice show almost zero theta enhancement after the choice, and vice versa. Neuroscientists classify this as an anatomical oscillatory double dissociation. This proves the MFC divides the work of cognitive control across distinct spatial boundaries. The medial wall utilizes this spatial partitioning to manage different stages of the decision cycle. Dorsal regions handle planning, and rostral regions handle evaluation. With the internal mechanics of the MFC mapped, we have to determine how these deep brain findings align with broader scalp EEG research. Historical data relies heavily on event-related potentials, or ERPs. Classic components like the correct related negativity are reliably recorded from standard surface sensors following a response, but their exact origins have remained difficult to verify. These heat maps track interchannel phase coherence, measuring how tightly the deep intracranial oscillations align with the surface electrodes sitting on the scalp. Immediately following the physical response, the data records a significant 20% spike in phase locking, specifically inside the theta range. The deep anterior theta oscillations are now firing in perfect synchronization with the surface electrodes directly above them. This empirical connection proves the classic surface signals studied for decades are directly driven by deep theta band generators working within the medial wall. The timeline of a decision is exact. First, posterior beta suppression stalls the motor cortex to assess the conflict. The choice is made. Instantly, anterior theta oscillations surge to evaluate the outcome, broadcasting that evaluation up to the surface of the scalp. Cognitive control is a dynamic process characterized by functional specialization, moving anatomically across the MFC. High-resolution intracranial data forces us to abandon simplified models of brain regions acting as single on and off switches, revealing instead a complex spatio-temporal network. If you found this breakdown valuable, please like the video, subscribe to the channel, and leave your suggestions for future neuroscience topics in the comments. This video was brought to you by Synestic Systems LLC, founded by Shane Persinger. As technology allows us to look deeper into the cortex, the gap between deep brain physiology and surface-level human behavior continues to close.